So in chapter number 8, we're going to talk about conservation of energy. So basically, I'm going to show you how we can use the energy equations to solve problems. Now, before getting into some examples, I'd like to talk about energy transfer mechanisms. So what you see on this picture here is just different examples of energy transfer mechanisms. So again, what this is showing you is that energy can be converted from one form to another. So for example, if you look at this energy right here, so electrical current is going to come here, and then the light bulb is going to use that energy to produce light, and then it's also generate heat as well. Or if you look at the cup of coffee, so some of the energy can be transferred to the spoon, and this process is called conduction. So these are just different examples of how energy can be transferred from one system to another. All right, so now we're going to start looking at some examples. So basically, we need to understand the different types of energies that we're looking at. So if you remember from the previous chapter, we said that there is kinetic energy, there is gravitational potential energy, and there is elastic potential energy. So this is an example where, so you have a book and you're just moving it from some initial height. Let's say from this initial height, so you're moving it down from this initial height to this final height. So we notice that at this initial height, it has some potential energy. Then when you move it from this point to this point, the potential energy is going to change. So we can say that the change in the kinetic energy plus the change in the gravitational potential energy has to be equal to 0. Then, so what we're saying is that there is going to be some gravitational force that is acting in this direction, and so we can use that to calculate the gravitational potential energy. So now, if we rewrite this equation, so if we say that the change in the kinetic energy plus the change in the potential energy is equal to 0, this is the same as saying that the kinetic energy at the final position plus the potential energy at the final position is equal to the kinetic energy before plus the potential energy before. Now, we can rewrite this equation in this form right here. So if you remember, we said that kinetic energy is just 1/2 times the mass times the velocity square. So if the energy of the system is not changing, so we have the kinetic energy after plus the potential energy after is equal to the kinetic energy before plus the potential energy before. All right, so this is an example. This is just a quiz. It's quiz number 8.2. I'm going to let you guys look at that just to review. I also want you to look at this example right here. So again, this is an example. If you give this mass some initial speed, because the height is the same, so if you want to calculate the so the speed, so if you want to calculate the speed just at the time when each of these balls is going to hit the ground, then we notice that by conservation of energy, because we're starting at the same height, the potential energy will be the same, and the potential energy gets converted into kinetic energy. So all the speeds will just be the same. So V1 is going to be equals to V2, is going to be equals to V3. All right. So now, generally, again, if you remember, we said that every system is going to have these 3 different types of energies. There is a kinetic energy, there is the potential energy, and the internal energy. So the internal energy is going to show up as just the forces of friction in the system. So for example, heat is an example of internal energy changes. All right. So we're going to look at this example, which is example number 8.2. And so this is a ball in free fall. So we know what the mass of the ball is. It's going to be dropped from some initial height h above the ground. So this is the initial height right here. And then it says that neglect air resistance, calculate the speed of the ball when it is at a height y above the ground. So we start from here. So at this point, y initial is equals to h. The gravitational potential energy at that point is mass times gravity times height. The kinetic energy is 0 because we start from rest. Then by the time that we get to this final point, the final height is y. The gravitational potential energy at that point is just mass times gravity times y. The final kinetic energy is 1/2 times m times v final square. So if you say that the sum of the potential energy plus the kinetic energy here must be equals to the sum of the potential energy and the kinetic energy right there, then we can set up these equations right here. So you can set up this equation and solve this equation to get the final velocity, which is just equals to 2 times the gravity times the height times h minus y. Now we can also calculate the speed of the ball by using the walk. So you can say that the walk done is just equals to the change in the kinetic energy. Now the change in the kinetic energy is 1/2 mv final square minus 0 because it starts from rest. Then the force is just the force of gravity. You multiply that by the change in displacement, and rearranging that equation, you can also get the same v final. So v final here is just going to be 2 times gravity times the height minus y. Now, so what if the ball is thrown downward from its initial, with some initial speed vi? So if we give it some initial speed vi, then by conservation of energy, we can say that v final square is equals to v final is equals to the square root of vi square plus 2 times gravity times the final height minus the initial height. Now notice that we could solve this problem as well also using the motion equations, but in this example we're using the energy equations by applying conservation of energy. All right, now this is the second example here. This is example number 8.4. And in this example, we have a spring-loaded system. And so what we have is that we have so this is a rifle. So it has a spring in it. And so at point A, the spring has been compressed such that the distance is equal to negative 0.12. So the negative here simply means that it's a compression. Now, when the spring is released, the ball is going to move past point B, which is the equilibrium point, and then it's going to rise to this final height right there. So we need to notice that at point A, the kinetic energy is 0 because it's at rest. And then at point C, the kinetic energy is equal to 0 because at maximum height, the velocity is also 0. So the kinetic energy would be 0 right there. So in this example, there is 3 types of energies that I need to be interested in. I'm looking at the kinetic energy of the system. I'm also looking at the energy of the spring, which is the elastic potential energy. And I'm also looking at the gravitational potential energy. So we can set up the system. So basically we're saying that the change in the kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy of the spring has to be equals to 0. So let's look at the change in the kinetic energy. So again, because it starts from rest and the final height is 0, so it means that the initial velocity is 0, the final velocity is 0, so the change in the kinetic energy is 0. Now the change in the gravitational potential energy is just equals to mg times y at C minus mg times y at A. So that's the change in the gravitational potential energy. Now the change in the elastic energy of the spring, so as this spring is going to stretch, the final energy is going to be 0, and the initial energy is just 1/2 times the k value times the x squared, where the x squared is just the value is the 0.12 because that's the amount by which the spring has been compressed. Now, so if you put all these equations together and you rearrange this equation, you can write k as 2 times the mass times the gravity times yc minus ya divided by x squared, And so solving everything together, you get a K value of 958 Newton per meter. Now, we want to find the speed of the projectile as it moves through the equilibrium position at point B. So what is the speed of this projectile just at the point where it passes point B? So when it passes point B right here, again, I can go back and write this equation as a change in the kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy of the spring. All of this must be equal to 0. Now, because it starts from rest, the initial kinetic energy is 0. The final kinetic energy is 1/2 mvb squared. Now, by the time that it gets to point B also, the y value is 0. So again, you have 0 minus mg times ya plus 0 minus 1/2 kx squared is equal to 0. And so if you rearrange all of this, you can get the velocity at point B is given by this expression. And if you substitute the values, you get a value of 19.8 meters per second.